In the study of electric field, we examined the electric flux through a closed surface and derived the expression of Gauss's law in electrostatics. Likewise, we define the magnetic flux in the same way. Please look at this figure. Consider an area element vector dA on an arbitrarily shaped surface. dA is perpendicular to the surface and has a magnitude of an area dA. The magnetic flux through the area element dA is defined as a dot product of B and dA, where B is the magnetic field at this element. Therefore, the total magnetic flux through the surface is the surface integral of magnetic field over the entire surface. The unit of magnetic flux is Tesla meter squared, which is defined as Weber. We consider a special case where a plane of an area A is placed in a uniform field B. B makes angle theta with dA. The magnetic flux through the plane in this case is equal to BA cosine theta. If the magnetic field is parallel to the plane as shown in the figure, in other words, if the field is perpendicular to the normal to the surface, then theta equals to 90 degrees and the flux through the plane is 0. On the other hand, if the field is perpendicular to the plane, in other words, if the field is parallel to the normal to the surface, then theta equals to 0 and the flux through the plane is BA, which is the maximum value. Now let me give you an example. Please look at the figure. Here is a long straight wire carrying a steady current I. A rectangular loop of width A and length B is located near the wire. The distance between the wire and the closest side of the loop is C. The wire is parallel to the long side of the loop. We wish to find the total magnetic flux through the loop. We know the magnetic field lines due to the long wire are circles, which are passing through the rectangular loop. The magnetic field is inversely proportional to the distance r from the wire. Therefore, the magnetic field is non-uniform over the area of the loop, and we must evaluate the flux d phi through a differential area dA and integrate d phi over the entire surface. We choose the area element dA of length b and width dr as shown in the figure. The magnetic flux can be calculated by this expression. Noting that B is parallel to dA every point in the loop. B dot dA is B dA. We substitute B by this one and dA by B dr. Integrate over the limits from C to A plus C and obtain the flux. Based on Gauss's law, we know that the electric flux through a closed surface is proportional to the net charge enclosed by the surface. In other words, the number of electric field lines leaving the surface depends only on the net charge in the surface. This is because the electric field lines begin with the positive charges and end with negative charges. The situation is quite different for the magnetic field lines, which form closed loops. Please look at the figure showing the magnetic field lines due to a bar magnet. Obviously, the magnetic field lines don't begin or end any point. For any closed surface such as the one outlined by the dashed line in the figure, the number of lines which enter the surface must equal the number of lines which leaves the surface. Therefore, the net magnetic flux must be 0. This situation is totally different from the electric field lines shown in this figure. For any closed surface, the electric flux is not 0 if the net charge is not 0. Now we arrive at Gauss's law in magnetism. Gauss's law in magnetism states that the net magnetic flux through any closed surface is always zero, which is expressed by this equation. This statement also indicates that isolated magnetic poles have never been found in nature. The magnetic field we are exploring is the field of free space. What if there is a magnetic materials in space? Let's explore it next lecture.